You're sitting right there in your Cambridge IGCSE physics exam, paper 0625. You flip the page, see a seemingly basic electrostatics question, and think, easy, I know this. You jot down a quick answer and confidently move on. But then, results day hits, and you realize you've dropped crucial marks on a topic you literally thought you had mastered. So, what went wrong?
Okay, let's dive into this. I want you to mentally lock in your answer to this scenario right now. Let's create some instant stakes here. When a polythene strip is rubbed with a cloth, why exactly does it become negatively charged? Is it A, because it magically creates new electrons out of nowhere? Is it B, it gains electrons by friction? Or is it C, it loses protons? Go ahead, lock in your choice.
So, if you picked B, awesome. You've definitely got the right concept in your head. But here is the massive shortcut warning that traps thousands of focused learners every single year. You simply cannot just write vague phrases like charges repel or the rod got charged without actually explaining the physical electron transfer. Relying on this ordinary, vague revision shortcut, it's a really dangerous game and it will absolutely cost you those crucial exam marks.
Because your score for that vague answer? 0. Absolutely nothing. That is exactly how many marks you're going to get if you skip the scientific reasoning in Cambridge IGCSE physics. Writing a half answer based on some memorized shortcut is treated exactly the same by the examiner as writing no answer at all when it comes to the rigorous mark scheme.
Now in a moment, I'll show you the exact examiner clue that changes your answer completely. But first, you need the framework that makes that clue super obvious. Seriously, if you tune out now, you're going to miss the literal key to unlocking top marks in this syllabus.
Section 1. The Answer Framework. Upgrading to Mark Scheme Thinking.
Let's fix your exam strategy right now. This is the targeted system that transforms ordinary answers into bulletproof, Cambridge-approved responses. It's like a giant puzzle, and it breaks down into 4 non-negotiable steps. Step 1. You identify the core concept. Step 2. Locate the evidence or data provided in the prompt. Step 3. Apply your scientific reasoning. And finally, Step 4. Use precise examiner wording. Now, skipping straight to Step 4, just throwing memorized buzzwords onto the page, that is the fatal mistake. You absolutely have to build the foundational physics argument first.
Section 2. The Practical Investigation. Positive and negative charges. Let's move to and see how this builds.
We're going to apply this framework directly to that classic textbook practical. To run this experiment successfully, we need a very specific physical setup. Our apparatus requires polythene strips, cellulose acetate strips, a cloth to create that friction, some thread, a paper stirrup to gently hold the strips, and a retort stand to suspend the whole shebang in the air.
So think about the data generated from this setup. We suspend a rubbed polythene strip. When we bring a second rubbed polythene strip close to it, our observation is that they repel, they push apart. But if we bring a rubbed cellulose acetate strip close to that same suspended polythene strip, they attract. Pointing out this stark contrast between the 2 different materials interacting, that is step 2 of our framework, identifying the evidence.
And this brilliantly illustrates the core concept at play here, the electron. By strict definition, an electron is a subatomic particle that carries a negative charge and can be transferred to or from a material by friction. Notice the phrasing there. They are transferred, not created out of thin air. Friction actually moving these specific particles from one material to another is the real scientific reasoning you must state to satisfy step 3 of our framework. When polythene is rubbed, it literally steals electrons, becoming negative. When acetate is rubbed, it loses them, becoming positive. That transfer is everything.
Section 3. The Ultimate Contrast. Flawed versus top band.
Now, what's really interesting about this slide is the sheer difference in depth here. Let's shift into examiner correction mode. On the left, the flawed answer reads, the rod was rubbed so it got charged. The 2 polythene rods pushed away. I mean, it's factually true in a basic sense, but it gets 0 method marks, none. On the right, the top band answer reads, friction transfers electrons to the polythene, making it negatively charged. 2 negative, like charges repel. See the difference? The right side secures all the method marks because it explicitly names friction as the mechanism, electrons as the moving particle, and clearly links that resulting negative charge to the final repulsion.
Section 4. Interactive Viewer Challenge. The Gold Leaf Electroscope.
Let's escalate the stakes a bit with a harder, secondary piece of apparatus.
This is your pause and predict moment, okay? If a highly sensitive gold leaf electroscope is used to detect charge, why must we be incredibly careful about using good versus bad electrical conductors during our experiment? Really think about how different materials affect the physical flow of those electrons we just defined. Like, if you were to touch the top plate of the electroscope, what happens to the charge? Take a mental guess right now.
Well, here is the exact Cambridge-safe wording for the solution. An electrical conductor is a material that allows electric charge, specifically those electrons, to flow through it easily, unlike insulators such as plastic or wood. If you use a good conductor, like a copper wire or even your own bare hand, to hold your charged strip, guess what? The electrons will flow right through your hand and into the ground. The charge escapes, the gold leaf falls flat, and the electroscope detects absolutely nothing. So understanding the fundamental difference between the materials listed in the source is absolutely critical to proving your practical knowledge.
To really solidify that practical knowledge and nail the evidence step of our framework, here is a rapid-fire checklist of final examiner practical checks. First, you must ensure the suspended strip is completely stationary before testing it with the second strip. Otherwise, mechanical momentum just completely corrupts your data. Second, always identify your correct independent and dependent variables. And finally, remember that this specific practical presents minimal safety risk. That's a subtle detail, but examiners frequently use it to test if you've actually studied the physical environment of the practicals.
So, the crucial point is that mastering electrostatics is not about blindly memorizing rules. It's about logically proving the transfer of electrons using our four-step framework. You now have the framework for electrostatics, but what about the hardest data analysis traps hidden in your upcoming exam? Like, how do you apply this exact same logic when an examiner throws a complex, multivariable graph your way?
That unresolved gap is exactly what we are going to crack in our next explainer, where we'll reveal the ultimate safe shortcut to navigate those exact data traps. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Because honestly, if you can't logically prove your data, does having a framework even matter? I'll see you in the next one.